unit. Next we have to continue third year maths, and the subject is real analysis 1, unit 5, continuous functions on metric spaces. Definition: the function f is continuous at a belongs to r power 1 if limit extends to a, f of x is equal to f of a, f is continuous at a. The first condition is that limit extends to a, f of x exists. The second condition is that this limit be equal to f of a. So next example, the function f defined by f of x is equal to sin x dividing by x, x belongs to r power 1, comma x is not equal to 0 is not defined at x is equal to 0 and hence not continuous at x is equal to 0. So g of x is equal to sin x dividing by x, x is not equal to 0, x value is replacing 0. So substituting these values we get g of 0 1. So is continuous x is equal to 0 since limit extends to 0, g of x is equal to g of 0. Next we have to prove theorem. So if the real valued functions f and g are continuous at a belongs to r power 1, then so are f plus g, comma f minus g and fg. If g of is not equal to 0, then f by g is also continuous at a. Proof: since f and g are continuous at a, we have limit extends to a, f of x is equal to f of a, limit extends to a, g of x is equal to g of a, limit extends to a, f of x plus g of x is equal to f of a plus f of a plus g of a. So limit extends to a, f plus g of x is equal to f plus g of a. This proves that f plus g is continuous at a. A continuous function of a continuous function is continuous. Next we have to prove theorem. If f and g are real valued functions, if f is continuous at a and if g is continuous at f of a, then g composite f is continuous at a. Proof: we must show limit extends to a, g composite f of a equal to g composite f of a, or limit extends to a, g of x equal to g f of a. So given is greater than 0, we must find delta is greater than 0 such that modulus of g into f of x minus g into f of a is less than epsilon. So 0 is less than modulus of x minus a is less than delta. This is the equation number 1. So let b equal to f of a. Now by hypothesis limit y tends to b, g of y equal to g of b. Hence there exists eta is greater than 0 such that modulus of g of x minus g of b, that means f of x value is assuming x, g into f of a value is assuming b. So g of x minus g of b is less than epsilon, modulus of y minus b is less than eta. This is the equation number 2. Limit extends to a, f of x is equal to f of a. Thus there exists delta such that modulus of f of x minus f of a is less than eta, modulus of x minus a is less than delta, or modulus of f of x minus b is less than eta, modulus of x minus a is less than delta. This is the equation number 3. Thus if modulus of x minus a is less than delta, then f of x is within eta of b, and so we may substitute f of x for y in equation number 2. Hence modulus of g into f of x minus g of b is less than epsilon, modulus of x minus a is less than delta. Next topic is formulation theorem. the real valued function f is because at a belongs to r power 1 if and only if the inverse image under f of any open ball b of f of a is to epsilon about f of a contains an open ball b of a is to delta about a. There is f inverse of into f is to epsilon contains b a is to delta. Proof. It is of the utmost important that the reader fully understand before going on. Our final reformulation of the continuity concept will be in terms of sequences. Observe first that the sequence n varies from 1 to infinity converges to if and only if given epsilon is greater than 0 there exists n belongs to cap size such that xn belongs to caps b a is to epsilon n is greater than or equal to caps n, that is given any open ball caps b about a ball but a finite number of the xn are in b. Functions continuous. Next topic is functions continuous on a metric space. Definition. Let m comma rho be a metric space if a belongs to caps m and r is greater than 0, then b of a is to r is defined to be the set of all points in caps m whose distance to a is less than r, that is b of a is to r equal to x belongs to caps m rho of x comma a is less than r b of a comma r the open ball of radius r about a. Next we have to prove theorem. Let caps m be a metric space and let f and g be real valued functions which are continuous at a belongs to caps m, then f plus g, f minus g and fg are also continuous at a. If g of a is not equal to 0, then f by g is continuous at a. Proof. Only continuity at a point has been defined. The continuity of a function f at a point a is a local property. There is continuity of f at a depends only on what goes on near a. So now we shall define what we mean by a function continuous on a whole metric space. So next topic is open sets. Definition. Let caps m be a metric space. The subset g of caps m is an open subset of caps m if for every x belongs to g there exists a number r is greater than 0 such that the entire open ball b of x exists to r is contained in g. Thank you, students.